This program is brought to you by Stanford University.
So because this is the first seminar on marine energy, I have made it sort of Marine Energy 101. Okay, so I will talk about the actual energy that's in there, how you can extract it, who is playing a role, what are resource-based estimates, and so on. Okay, so very much an introductory seminar on this topic. Before I start, just want to point out that there's lots on ocean energy also on my website. I've got this blog called Smart Energy, and you can go to categories on the ocean power, and there's several interviews with people who are working in this area, and that will give you a little bit more information. Okay, so let's start with some very great optimism. If you read the latest numbers on wave and tidal energy, right, or marine energy together, then people are claiming that this is going to be one of the main resources in the world. And here are some of the latest. Looking at tides, it's a little bit disappointing at the moment, really. People see this, and we'll talk about that later. There's two ways you can extract energy from the tides, which we'll discover. One is potential energy, where you're really looking at the elevation of a mass of water because of tides, and you're tapping into that potential energy that is created every tidal cycle. But you can also look at the kinetic energy associated with tidal currents that are flowing because of these elevation changes in various parts of the globe. So these are estimated right now together to give about, say, 1,000 terawatt hours per year. You have to put this in perspective. There's about 18,400 terawatt hours that we are currently consuming. So that would be a small part of our global energy or electricity consumption and production. But waves are estimated to be fantastically high. Although what's very interesting is that the estimates range quite a lot, from 8 to 80,000. So we gotta be a little bit careful about this, and we'll talk about that later. There are other energy sources in the ocean that we're actually not going to talk much about. I really will focus on those three mostly, but there is also a technique called OTEC that looks at thermal energy and really derives energy from the temperature difference between the upper surface of the ocean and the deeper water. But I won't talk about that now. Very much also in the begin stage, but there seems to be a reasonable amount of energy there, but I think this will take a very long time. And then there is quite a new technique looking at the salinity gradient between fresh water, for example, coming from rivers, and salty water in estuaries, for example, using osmosis. So also very interesting topic, but maybe the topic for another seminar. So what I want to do today is see, are they right? Is this true? Where are we sitting here? Can we really tap into this resource? And can it really be one of the main resources in the world? Now, that was the good news. The bad news is that right now we're here. Ocean energy is on this picture. It is somewhere in one of those lines, because at the moment we're creating 10 megawatts out of a global energy production of 2.1 terawatts. So if you look at the percentages, there's a lot of zeros there. The other interesting thing is there's been about $500 million of investments in this particular energy and about $10 million of revenue. So that's also not so great. And these revenue numbers are very uncertain. I actually think it's probably a little bit less. What do we do about this? Well, there are more and more people who are investing money into this, though. And one of the things I wanted to point out that in September, the Department of Energy in the ERESA, which is the Energy Independence and Security Act, actually has allocated some money. This is almost the first for the US to go into this type of development. $7.3 million. They're sponsoring a total of 14 projects, 6 on technology development, 6 on market acceleration, looking at market barriers, how can you get these sort of systems going and accepted in the market, and then 2 by establishing national marine energy centers, and unfortunately Stanford is not on here. This is Oregon and the University of Hawaii. But what's interesting is that out of these 6 here and these 6 here, there are 2 local main players in this area, APRI here in Palo Alto, and also PG&E. and Revision is a consulting company that's in Sacramento. So there's a lot of local interest in this also. There's also a lot of opposition. This is a protest march that was going on in Mendocino against the WaveConnect project that PG&E is trying to start. In Mendocino County, there's good wave energy resource, but the locals weren't very happy with this. So there's all sorts of politics going on here as well. So what I want to talk about in the next 35 minutes is, what's the big deal? Can we be optimistic, or should we be a little bit careful? So I'll start with the Marine Energy 101, talking about the various types of energy that are out there and how we can capture this. Closer look at the resource base, global and also in the US. And I'd want to focus on the West Coast specifically, because there's lots of stuff in the paper here on West Coast marine energy devices. Talking about the main players, who would you want to work for if you want to enter in this area. And then lots of really crazy energy devices. This is probably the most creative energy area, I think, at the moment. And then looking at some challenges and maybe putting some disclaimers and some question marks with some of the designs that are out there right now, and lots of opinions on the way. Okay, so wave power 101. Let's look at waves. Here is a schematic of a wave. It's in a certain water depth, got certain wavelengths, got a height. Water particles are just being pumped up and down, and people have been thinking for a long time now, how can we tap into that energy, right? So there's constantly various places in the ocean, big masses of water are being lifted up and then lowered again. So every time potential energy is being created. Now, how would you tap into that? And how much energy really is stored in this? So there's all sorts of different wave periods and wave amplitudes. Of course, in reality, it doesn't look like a beautiful sine curve. In reality, you have all sorts of different waves going on with different time scales. So when we're assessing a wave power resource, we don't look at one particular or sort of a simple average of wave heights, but we look at something called HS, which is the significant wave height. And sometimes people say that's the I-norm wave height. When you're looking out over the ocean, you tend to see the larger waves. HS is about the average of the highest third of the waves. That's sort of what you see. Okay, so the eyeball estimation is a good one for this. And then you're looking at the sort of an average period, an average what they call zero crossing of these waves, and you use this in a formula that gives you sort of energy contents per crest length, per meter of crest length. So here's a wave coming in, and every meter of that wave will contain this many kilowatts. H squared times the period T, okay? So in this particular example, where HS is about 3 and the upward zero crossing is about 10, we would have about 45 kilowatts per meter contained in this, okay? So this is the total energy, and of course if you put an energy device in this wave, you will not get that much energy out of it, but that is what the energy density would be. So let's have a look and see if we can get some energy out of Half Moon Bay Maverick, right? So this is a Maverick. So what if we once a year or so put that in there? So you have, say, 15-meter high wave with maybe a period of 20. That's just a guess. I'm not quite sure what it is. And maybe a crest length of about 50. Then you would get 112 megawatts. So now we're talking something, right? Now that's a lot of energy. Okay, now what about the tides? Well, this is probably, you've all seen this before. Tides, tidal currents are formed because of power or force balance, and there's 4 types of forces that play a role. Mostly people say, well, it's because of the gravitational force of the moon. But there is also on water, gravitational force of the Earth. Then there are 2 centrifugal forces, one of the rotation of the Earth around its own axis, and one because the Earth-Moon system is rotating around its center of mass. Okay? And that center of mass is indicated right here with a big dot. And here are these 2 rotations. And here's some other numbers. If we do the mathematics, then we get those 4 forces out of it. And if we put that all together and look at it, then we have this sort of system where the ocean, if the Earth was covered completely with water, would bulge on either side of the moon. So here's the moon and the sun. So not just on one side, and we have what we call a semi-diurnal tide. But of course, because of location of land mass and so on, this is not quite the case. Most places that people are interested in putting wave or tidal energy have a semi-diurnal tide, meaning I have a high tide twice a day and have a low tide twice a day. But there are also areas in the world where it just have a diurnal tide, where a high tide just occurs once. Okay? Now, there are some dramatic tidal flows around. The main example that's always put, or there's two examples. One is the Severn estuary in Britain that has a fantastic tidal range. Now, elevation gain is meters high. And the other one, which is really the champion in the world, is the Bay of Fundy. That has, I don't know if you can read this, but it has tidal elevation of 14 or 15 meters. So difference between high tide and low tide. So that's an incredible amount of potential energy that you could tap in. And the Bay of Fundy has been the topic of many, many discussions, tidal and also wave energy systems. Some of the places in the world, you have absolutely fantastic tidal flows. This is one in the north of Norway. And this particular one, the Maelstrom of Solstormen, goes with about 20 knots. So this is a 20-knot current simply because of tidal motions. And of course, if you could tap in that would be very nice. Because as we'll see later, the power that you can derive is proportional to the velocity cube. So if I have something going at 20 knots and I cube that, there's a lot of energy in there. So let's have a look now at sort of the current estimations of the resource base at a bit more detail. So if you're looking at wave, it's not equally distributed, as you can see. The more red, the higher the energy content. Most people are doing things between sort of 40 and 80 kilowatts per meter wave energy density or power density, not below. Then it's not worthwhile. A world-class resource is said to be about 60 to 80. One of the things that you will immediately see is there's a lot in Australia and there is a lot in northwestern Europe. And this is one of the reasons why the UK and Ireland, Scotland, are really the main places where developments are happening. Another thing, higher power density can normally be found in deeper water. So we go 50 meters or deeper, we're generally better off. So that's one thing to remember. So if you really want to tap into the waves, you go offshore quite a while. And the other thing to remember is that waves are very seasonal. For example, at the West Coast, we have very little wave energy in the summertime, but pretty good wave energy in the wintertime. So this is some sort of predictable intermittency that we have to think about when we're designing wave energy resources. Tidal energy, the distribution is actually quite similar. Here what I show you is average tidal elevations. This was based on satellite data from NASA. And of course, these are not quite the same as tidal currents, but here are places where you could tap into potential energy, no elevation differences. And I just want to point out the black, very high elevation gains here in France, which is where the first potential tidal energy device was created, and we'll have a look at that later. And again, we'll see brilliant resources here around the British Isles, also pretty good near Alaska, now in Canada, and then of course here in this area with the Bay of Fundy, which we've talked about before, right? There's a tremendous resource there. So how about North America? Let's have a closer look. So this is the wave resource base in North America. In total, estimated in terawatt hours per year. Here are some of the numbers per crest length in the kilowatts that we talked about earlier. And we see there is a big difference between the West Coast and the East Coast. West Coast is pretty good. Now, not world class, right? It's 20 to 30 kilowatts per meter. World class would be a little bit more, but good enough to really look at this and see if we can do something with this. For example, California, say 20 kilowatts per meter, but we have 1,200 kilometers of coastline. So if we don't mind giving up a coastline and putting tidal devices everywhere, we could get quite a significant amount in there. But again, these ones are very, very seasonal at the West Coast. Okay, so it's really winter energy that we could get. Taking that all into account, the estimates for North America are that we could get about 7% of our consumption from wave energy alone in the not so long future, right? So maybe in the next 10 years, 15 years. And 7%, you see that it's about the same as hydro. Now, there are people out there, for example, APRI and NRL, who think we can do this maybe in 5 years' time, but that's what they said about biofuels also. Not so sure about that, okay? I think they're being way too positive, but of course they'd like to get more funding. So it serves them to say these things, okay? What about tidal? Tidal seems much less attractive. I mean, look at, here, this one in terms of the terawatt hours, you see in the hundreds and maybe 1,000 terawatt hours per year. When you look at the tidal resource base, those numbers are very much smaller, okay? So it doesn't look so great tidal-wise, but there's a couple of things that I want you to remember. First of all, they're not seasonal. They're very easy to predict. The other thing is also that locally, they can have extremely high power densities, right? So it's very much more localized than wave power. And so if you have an isolated community with a lot of this very high power density, it may be really worthwhile putting a tidal energy device there. And the other thing I wanted to say, and this is where we'll come in at Stanford later, is that the research is still very uncertain. So people have estimated this, but I put some question marks in it. I actually think it's probably quite a lot better than they're thinking. Good question to ask is, how does this compare with wind and solar? So here's just a table where I put some of these things together. And here I put in concentrated solar panel as a comparison. Some power densities compared. Now it's a little bit hard, of course, to compare apples and oranges for the best resources. Intermittency is an interesting one. In tidal currents, of course, we have intermittency because tidal cycles every day. And also, you know, these tidal elevations, they of course change over time also. There's another cyclical period there where the tidal elevations go up and go down. Wave, we have local winds and swell from distant storms that determine how much the wave energy is. Wind, of course, we have fronts and storms coming through, and solar, we have all sorts of other intermittency issues. One of the interesting things is the difference in predictability. So with solar can change, of course, well, minutes, it may be a little bit exaggerated. But wave and especially tidal currents are predictable very far in advance, okay? But definitely wave and tidal currents are still pre-commercial. And of course, wind is commercial and solar CSP is already early commercial. So let's look at the West Coast. If we just look at this West Coast, there's so much going on about this right now. Here are some estimations. I used here a 15% extraction rate of the energy that's available. So for waves, that would mean that 15% of the coast will actually put one of those devices. Very unlikely that we'll do that, but hey, just for comparison. And then this gives you the percentages of the electricity production that we would need at the West Coast, okay? Now wind, if you talk to Mike, for example, would say, hey, that's a lot more because we can extract more than 15%. But just for comparison, I put the same there. Okay? Again, a bit of a disclaimer, tidal currents, we're really not so sure. I think that may be a little bit more. But if you're looking at, for example, the Mendocino coast or the Golden Gate area, you know, and you look at what's available, my gut feel is that we're much better off putting wind there, offshore wind, than we are putting wave or tidal devices. Okay, so who is developing devices and at what stage are we? Here are the players. Okay, so on the world map, the bigger the circle, the bigger the player. Big fat circle in the UK. Not so bad in the US in terms of the number of technologies that we're developing. and there's more and more interest in the US also. More and more money goes into this. Venture capital is gone a little bit crazy, and we'll see that later in 2007 and now also in 2008, putting a lot of money in this. I mean, I've looked at devices that were proposed, and venture capitalists have said, oh yes, we're going to fund this, and then you realize it's actually not a very good device, but they still do it. So I should just shut my mouth at that point, right, and let them invest, because it will always lead to something. So here, the UK and the USA, definitely major players in both ocean wave and tidal current. There are some developments going on in salinity gradient, this osmosis project, and also OTEC, which is the temperature gradients, but not so many as the others. We are, I would guess, about 20 years behind wind turbines. Here are some technology development curves of photovoltaics and windmills and gas turbines with an opening cost and then a cost reduction as we went on. So this is for installation costs in dollars per kilowatt. It's a little bit hard to say where we are right now with tidal and wave, because we have very few numbers. You know, people don't really give you those numbers because it's so early on. My guess is, and most people's guess is, that we're about here where windmills were in 1982. Okay, and then hopefully the costs will go down. But how fast? That's the question. Investors, though, are buying into it, as I was saying. Here is the annual investment in the world in blue per year, and then the cumulative investment in red. And you can see that especially in 2007, we had almost $220 million invested. And really these investments started in about 2001. Okay, so every year it's growing. 2008 number was for earlier this year, so this is up to the month of April or May. Of course you can't read this, but this is a list put together by Roger Bedard from APRI of all the wave energy devices currently on the market. And there's in the 30s, I can't talk about them all, so I'm just talking about the ones that I think are most fun and most promising. So one type of device is what is called an attenuator device, and the Polamosh sea snake is the big example. This is also the first commercial wave energy system out there. There's none other, well, there's one other that has some commercial value at the moment, but this is really the first one. They have something running in Portugal now for about 2 megawatts, so not very much. It's a medium-sized wind turbine, one of them, right, that delivers that same type of energy. They have a power purchase agreement with the government, so it's sort of a feed-in tariff, which is set at about 28 US cents per kilowatt hour right now. So that's the cost at this moment, right? So that gives you a sense. Again, real cost data are not really available, but this gives us a sense of what's there. They're building something in Orkney in Scotland of 3 megawatts, and they're planning a 5 megawatt device in Cornwall. So still very small numbers. And this has cost them about $70 million so far. So what is it? It looks like a sea snake. It's a big thing, about 3.5 meter diameter. I saw it in Orkney. Big thing, several sections. And in between the sections are joints, and the waves push these joints up and down. And in the joints there's hydraulics. And as it is being pushed up and down, fluid is passing through, going through a hydraulic motor, and that drives the generator. Right? So that is what it is like. So one of them gives about 750 kilowatts. Okay. You can also have what they call point absorbers. So they also absorb this up and down motion of the waves, but not like the Polamosh over quite a long stretch, but just locally at one point. The first one is called the power buoy, which is a nice name. And that is the first publicly traded wave company. So they're not as commercial as the Polamosh Wave Power Company. But Ocean Power Technologies, which is a US company, is now trading on NASDAQ under OPTT. When they became public, they generated about $90 million. Okay, so that's reasonable investment. They don't have that much, really. I'm really interested in those sort of numbers because at the time when they went on the market, they really only had one test device for 40 kilowatts, in Hawaii and one in New Jersey. So there's not that much out there, but investors were buying it. Okay, so this power buoy, again, it's being lifted. There's a lot of machinery underneath, and we'll see that on the next slide. It's been lifted up and down by the waves, and it extracts that sort of potential energy, if you like. Ireland has one too. That's a cousin called Wave Bob, which probably is my favorite name, because it bobs on the waves. They are in, it's wavebob.com. They're in Ireland, the UK, and the US. Big thing also, this is 20 meters. That one was about 11 meters. Can generate about 500 kilowatts. And underneath is this whole contraption here, that as this is lifted, this moves also up and down, and that energy then is stored. Okay. It's been tested. They've really only built one prototype, and now they're planning a commercial wave farm, but they're not getting there. But they have a lot of investment and a lot of support from the Irish government. Now, you don't have to go on the ocean. You can also go into the surf and extract wave energy from the surf. And one way to do this is what is called an oscillating water column. This is old technology, but there is a company called Wavegen in Scotland that has designed quite a new modern oscillating water column, and that's why I put it down. And they have one prototype right now, 500 kilowatt prototype in the Outer Hebrides in Scotland. And they're planning a big system, 300 kilowatt system in Spain. So not such a difficult technology to understand. Here is a chamber that they created near the surf. A big waves comes in. Water is pushed into this chamber, pushes air out through a turbine. Now, and then when the wave retreats, it sucks air back in through that turbine. So then these turbines can run both directions of airflow. Okay? So it's really an air turbine, but the air is being driven through the turbine by water replacing its volume in this chamber every time a wave comes in. So very, very simple engineering design. And all they really needed to do is design a turbine here that works well in both directions, right? In both flow directions. Okay. Okay, so just putting for the wave devices some comments together, some pros and cons and some uncertainty. So I think one of the pros is certainly that these wave devices are very widely employable. You can go offshore, you can put it basically anywhere. If you have point absorbers, you can put them scattered around offshore, out of sight. There's reasonable scalability. You can make farms of point absorbers, so of Polamosh farms, just by adding lots of devices to a local grid. The resource estimates are relatively high, especially compared to tidal. The waves mask noise. This is one of the things that they use to sell this. Noise pollution is very low, but I think it's a bit ridiculous to list. But anyway, I wanted to list it anyway. And it's more predictable than wind. So those are the good ones. Now, what about the negatives? It's not as predictable as tidal, and it is seasonal. But this is one of the main things. The wave fields that are out there are very chaotic. And that means that as an energy device, you cannot just use a design wave on which to optimize your device. It has to work well for an enormous variety of waves out there. Okay, so the tests are very interesting here. You really need to go into the ocean to test it. Of course, there's a very demanding physical environment. You're remote. You're often in hostile areas. You're up in Alaska. You're up in the Hebrides. Not the nicest climate offshore to be in. And of course, you have salt water in which these things are operated. And every time you have moving parts and salt water, it's not a pretty sight, right? Because there's corrosion, and you have to really be careful in design, and that just adds design costs. Also, forces because of the water currents are relatively high because the density of water is so high, much higher than air. So you have to take that into account also. One of the big negatives at the moment in a lot of countries is regulatory barriers. In the US, for example, the Federal Energy Regulatory Commission, the FERC, uses most of the hydropower regulations also for wave or for marine energy. And so they're not really applicable to it, and there's a lot of work going on right now to remove some of these barriers. And the other thing is, of course, that since they're often in remote areas, you have very high infrastructure costs, right? Putting a grid down there, putting cables underneath the seafloor to a land-based infrastructure. Now, these are all uncertainties. Environmental impact is really still uncertain. Of course, with the oscillating water column, it was pretty clear what it does or what it doesn't do. But if you had a whole wave farm of Polamosh, people don't really know what will happen to local currents. If you extract the energy, does it have an effect on the local environment? Don't really know. What is also uncertain are performance and costs. Very, very hard to get good data because we're in such a baby stage, and everybody is trying to get venture capitalist funding, so they keep this often secret. And there are big market barriers, very high costs right now per unit. And so maybe one way to resolve this is going to feed-in tariffs, which is actually happening right now in the UK. And then the other thing, which not a lot of people talk about, but makes a lot of sense, if you had a device like this that works on waves that vary all the time, so the power density fluctuates all the time, then integrating that into a network, a power network, that's an electricity network, that's not simple. And so you really have to think about this. Also, there's so many different devices out there. They all use different types of engines. They all have different types of power output. And there is nothing common. There's no common design, for example, for this is how we deliver power to a network. Okay, so how about tidal? Now, this is potential energy from tides. And there's really only one big one. This is always mentioned. It's in La Rance in France. It was built in the 1960s, so it's been around for a very long time. 240 megawatts, and it's been running about 10 to 20 cents per kilowatt hour, okay, depending a little bit on the tide. So that fluctuates, of course, a little bit. So the idea is that in the estuary, when the tide is rising, so here the tide is rising in the sea, here's my estuary, you have a main valve open and you just let the water flow in at high tide. So the water flows in, turbine here, nothing happens through the turbine, this valve is closed. And then when you have an ebb tide, you close the valve and you're letting all the water flow back out to sea on ebb tide through the turbine. Okay? So it's a simple, very simple idea. One of the big problems, of course, is not just the water that flows back through the turbine, it's also everything else, like fish. Right? And the other thing is also that, of course, when you do something like this, you heavily impact all sorts of sediment transports, fish migration, so you're completely changing the environment of the estuary. And this is one of the reasons why after the La Rance, people have just not built this. There were lots and lots of plans. It got a lot of publicity at the time. People were very excited about this. There's so many places that you could do this, but it's not happened. Right? It's a very, very few. There's one exception. Korea has planned to build a really, really large tidal barrage, and they're really building this right now. It's going to be something like 3 gigawatts. Right? So they are doing it, and they're probably not as concerned with environmental consequences. But everywhere else, it's been a disaster. For example, the Severn, they've been talking about this forever, to put a big tidal barrage in the Severn, and it's always voted down. So now they're looking into tidal turbines there instead. So what about these tidal turbines, or tidal currents? They're really sort of submerged wind turbines. So this is the windmill in the village where I grew up, and when the sea level rises, we're going to be okay, right? So they're just going to be underwater and giving us lots of energy, right? Now, what's happening at the moment it looks a little bit different, a bit more sophisticated, maybe. So here are some of these submerged wind turbines. Here's a schematic artist impression of a wind farm of these guys. Those are the CGen, built by Marine Current Turbines in the UK. It's now being tested in Northern Ireland, and I just got the news flash this morning that they put it in June. It is the real first commercial wind turbine farm, and after a week the blade broke, but they've just replaced it. So apparently now it's running, and we're going to get some data. Okay. How much energy can you extract? Well, let's simplify this a little bit. Suppose that here is the turbine area. Okay, so here's the turbine blades rotating, And if you look at the kinetic energy of all the water that flows through this turbine per second, then that would be, using just kinetic energy, half times the density times A times V cubed. Okay? So here is that V cubed relationship between velocity and power. That's enormous, thinking about a density of water being very, very high. So the good news is the density of water is high, so the energy density here is really, really large. That also means that you don't have to go to very large blades, right? Which you don't want underwater anyway, because then you have some problems with fish and other types of creatures there. So most of the designs, the blades are about 10 meters, okay? Not 100 meters or so, which you have in the big wind turbines, and you get the same type of power out of it. The bad news is the density of water is high, because there's tremendously large forces. Now, on the base, for example, which you have to put those turbines, much, much higher than you'll have in wind. And there are other problems. Here are some of the unique problems. So you cannot simply submerge a wind turbine. Unfortunately, most of the, if not all, of the designs that are out there right now are really just beefed up wind turbines. Now, they look at the wind turbine, they make it a little smaller, about 10-meter diameter, and then they just beef it up to deal with the extra forces. So they're really monstrous things when you look at it from an engineering design. Here are some of the specific issues that you'll have with a water turbine. Blade strength, fatigue, and vibration issues, much, much bigger problem than in wind turbines, is one. One of the things is when you go in the coastal area, for example, you have changes in fluid density that are non-negligible. In air, you can neglect these things, but in water, you cannot because of salinity. Okay? And so when the blade turns, it goes through gradients of density. And that gives you forces on these blades, extra stresses that are very hard to deal with. And then you have tremendous added mass effects that are much stronger, of course, when you're displacing water than when you're displacing air. The other thing, which is really the big thing, is that you have great susceptibility to fluid cavitation, especially at the blade tips. Now, these blades don't go so fast, so you may have a 10-meter blade going about 10 RPM or so. But still, that blade speed is reasonably high, of course, when you have a 10-meter blade. And very often cavitation occurs, and cavitation, first of all, it makes a heck of a noise, but then maybe say, okay, that's not such a big deal. But it really damages the blades very, very quickly. Right? So we have to be very careful. Then the other thing is you have constantly varying flows. You've got boundary layers in these coastal ocean regions that you have to take into account. You have bathymetry effects that can create eddies and all sorts of interesting turbulence. And of course, you have bidirectional flow because of the tides. You know? And moving these things around is, again, it's another moving part in this salty environment is not so simple. Okay? And so the design of the support structure for the turbine is a very big thing. Now, what they do at the moment is they use very, very simple fluid mechanics models to simulate this. Most of them are derived from wind turbine design also. And what we really need is improved coupled computational models, which we could actually do here at Stanford. So that would be very interesting. So the CGen, I talked to you about this before. There is one installed right now right here at the entrance of this estuary here in Northern Ireland. They're also talking to Vancouver, so we're going to see one pretty soon. They were earmarked for the Golden Gate Bridge, also here in the Golden Gate area in San Francisco, and they're talking to Bay of Fundy, so that's MCT. And then there's another design, open hydro, very different type design, where you actually have water, this is empty, and you've got blades sort of rotating on the outside. So this gives you some improved power efficiency, and you have a reduced risk of resonance failures, but there's some other problems associated with these types of designs. And in America, you have another company that's working in this area right now. Now, where are these things tested? There is only one test site right now in the world, and that's EMAC, the European Marine Energy Centre in Orkney, Scotland. And I was there in August, so that's my, it's a very beautiful place. They've got a wave test site, and they've got fantastic waves, up to 15 meters, Atlantic waves coming in. No, but a great wave spectrum, so you can really test your energy devices very well. They have a tidal test site, and it's a wonderful tidal test site. They have up to 8 knots of tidal currents. Okay? So this is world class. What they've done is they put these berths out there in the ocean that have sea cables already connected to an onshore facility. And so people don't have to worry about grid connection. The grid actually, that local grid, connects to the national power grid. So whenever they're testing, they're actually using the electricity. So that's nice. Of course, it's very expensive electricity. But they also give assessment of energy conversion, structural performance, and survivability. So it's a wonderful site sponsored by the EU. Here is that location of Orkney, for those of you who've never been there, up north of Scotland. And here are the locations of the sites. So the wave test sites is Ballycrew, where I visited, and then here is a tidal test site also. Okay, so now let's look at sites and designs, how they're selected. If you want to assess a local resource, you need quite a lot of tools. And most of this has not really been done very well. So when they're looking at a site, first of all, you want to get some idea of wave and currents. Most of the time now people just look at weather buoys. But if you really want to have a good estimate, you need to use something like HF radar. Now the good thing is there's a lot of radar out there for military reasons. And the bad news is they don't really want you using it all the time to look at different frequencies than those from enemy submarines, right? So there's 2 HF radar systems in the world that are used, Seaview Sensing, which is UK-based, and CODAR, which is California-based. When you have a sense of whether you have a world-class resource, you may do some 2-dimensional tidal modeling, very simple tidal modeling for sort of initial site ranking. But then you really need to go to a 3-dimensional full tidal modeling for design optimization, because you need to take into account what's happening in the depth because of bathymetry effects and so on. Now here we can come in. It's a big investment, but there's a code at Stanford called Sundance that I'm also working on that could be used for these sort of assessments. Then you need to do environmental impact studies. This is really at the infant stage. If you ask me, what are the environmental impacts, I'd say nobody knows. There are some reports that say from a lab test, they do this in the lab also with the wave test, for example, or the tidal turbine test that say, well, there's a lot of erosion going on near the turbine. There's a lot of extra or different velocities that are created, but nobody really knows. I don't believe some of these studies, and I don't think they're necessarily scalable. Now, if you do this in the lab, it doesn't mean that the same thing will happen at the actual site. So we really need to look at this still. And then site optimization is interesting. First of all, of course, you need to have a good resource, but there's also often navigation channels, so you need to take that into account. You have fisheries, and then you have lack of infrastructure. So there's lots and lots of things that we'd have to do. Now, they've been through an exercise like this here in San Francisco for years now, right? It started quite a long time ago to see if they could do something with the Golden Gate. So here's the Golden Gate Bridge. There is a wonderful canyon here, the Golden Gate, which funnels a lot of the tidal flows into the bay, San Francisco Bay. And there's really nice tidal currents. I don't know how many of you have sailed on the bay, but it's actually really, really hard to sail against the tide, right? You have to know your tides, otherwise you get stuck on the ocean. So the speeds are about 4 to 5 knots in most places. So that's a really nice site. It's best here on this sill. There's this little sill sticking up here, right in the middle of this almost underneath the Golden Gate. And there you have the highest power density. So they were thinking of building a turbine right on top, right here, and seeing if they can extract some things out of it. APRI came in a couple of years ago and did a study, and they said, oh, there's enough. There's about 20 megawatts, maybe even 100 megawatts. But then there was a new study done by the Public Utilities Commission, just released in March, and they said, no, it's only 1 megawatt. Which is exceedingly little. So I don't know. So we're looking at this now to see if this is true or not. Here is one of the power density maps that they created in this latest study with the Golden Gate Bridge, and then you see some high power density in this area here, but unfortunately you're all stuck with shipping lanes, and then you see a little bit more just right near the Golden Gate and the sill there also. So I don't think it's going to happen in San Francisco. If you can only extract 1 or 2 megawatts, you'd be silly to go through all that expense. You could just put a wind turbine somewhere, right? And you don't even need such a big wind turbine. Okay, so what's the verdict on tidal current devices? Here, high predictability, high power density locally, low visual impact because you're putting it subsurface. And I put this on again because, of course, any noise is masked. The cons, well, design exceedingly challenging, site selection very involved, demanding physical environment, again, regulatory barriers, high infrastructure costs, and so on. And the uncertainties are very much the same as with waves. Okay? And one big uncertainty is environmental impact. But we can study this. Now we can suss this out. And I think that if I look at what is the most fun for us to work on here at Stanford, for example, is definitely in the design and the site selection. Lots of optimization to do, lots of turbine optimization, shape optimization, tidal flow modeling, and so on. So we could do that. So what I think, in conclusion, looking at it right now, it's really just the technology is very basic right now. Okay? People are just starting to think about this. But there's lots of activity and there's lots of new ideas coming. All the current devices are a little clunky. They're over-engineered because they don't really know what to do with these strong forces that you have in water. But I think that will improve very quickly. If you look at old wind turbines, now from the 70s or so, it was the same then, there. Okay? So we shouldn't judge on that. But it's expensive to develop them. So potential is certainly there, especially in wave, possibly in tidal. It's very attractive for local solutions, for example, isolated communities. Wave and tidal current devices, I think, are definitely most promising in terms of environmental impacts and resource base. Technology, as I said, is really pre-commercial, but it's growing fast. And this is really, for me, one of the exciting things. It's very challenging scientifically to look at and work on these devices, and potentially rewarding. And we can certainly play a role, especially in the tidal current technologies. Okay? So that's my overview, and I'll be happy to answer any questions you have. Huh?
One of the technologies that put wind farms on that is developing a variable speed drive pump.
Yeah. Mm-hmm. Right now, nothing of that is driven by universities. Yeah, but companies definitely are working on that. I mean, all the tidal turbine devices have something like that in them, but it is mostly an adapted design from the wind energy. Yeah, and this is one of the design challenges that we still have. Yeah, definitely. It's all part of the design optimization. Yeah, it's a good area. John?
So you mentioned flow design. Do you know if what they're doing for water is like those ducted fan things?
Yeah.
They do for air? It's like that?
Yeah, they're basically taking their wind design and just submersing it.
Because at least that's, if what they say is true, at least it sounds like it's a little better flow.
Yeah, but there are some other problems with it in water. For example, cavitation problems don't go away. In fact, they may be higher. There's some other things that they haven't really looked at very much. Also, their design is very much, there has a lot of moving parts. And when you're going underwater, you want to limit that a little. So I don't know. But yeah, in fact, there's some people here that are talking to them about this also. Yeah. Yes?
Excuse me. Are you looking at run-of-river kinetic type energy harnessing as well? What are the same?
Those are river systems. Yeah, I mean, a lot of those are in development. I'm not looking at that myself. No, I'm looking at coastal ocean modeling only. But there's been a lot of new devices also in there, run-of-the-river type devices, as well as river turbines, right? They're certainly looking at that.
Why are they designing the turbine blades more like an air turbine blade, not just like a propeller in reverse almost?
Because the companies come from the wind energy field, right? And they really just have taken these big wind blades and put it in there. Some companies are coming out now that scale up propellers. So most of the propeller designs are very small, very high RPM. That is not good for power generation. So you can either take a wind turbine and try to make it suitable for water, or you could take it and scale it down and beef it up. Or you can take a propeller design and scale it up and slow it down. Both of those cases require you a complete blade redesign.
But like the largest cargo ships in the world have like, I don't know, 10-meter blades and then like 100 RPMs or something.
Yeah, and so there are people there. In fact, I don't know if you noticed, but on one of the titles it had a little primer, little plug for an energy seminar here in January, where we have Julie Young come in, who's a professor at Princeton University, is a propeller expert. She's probably one of the best propeller designers right now in academia. And she is moving into this area and really using her propeller design knowledge to do this. And the main thing that she brings with her is a much better software tool. And in fact, we're working together. I'm coupling the coastal ocean code to the wind turbine code, right? Because if you really want to optimize your design, you need to have this coupled to a larger scale code also and embedded. So there's definitely movement there. The companies, though, that are in there and they're working in there just have been coming from the wind energy. And when you look at the models that they use to optimize this, they're very simplistic potential flow type code models. Right? Very simple. Yes?
So with the threat of rising sea levels, there seems to be renewed interest in tidal barrages as
Yep.
protection for cities. You think, is that also going to bring up renewed interest in tidal power generating systems, like turbines within those barrages? Have you come across that yet, or are the two things not met up yet?
There is some renewed interest in tidal barrages, right? I mentioned Korea. One of the good things about Korea is that, but we can't really read about it. I haven't found any papers about this or any other technical reports, that they are completely redesigning the turbines in their very large tidal barrage. Now, if they do a really good job with that, that may also be a turbine that you could use as a tidal turbine, separately. Holland, we're very concerned about sea level rise. 40% of our country is already below sea level right now. So I grew up 5 meters below sea level. They're definitely talking also about tidal barrages. We have, of course, in Holland already several systems, our storm systems that keep storm waters from coming in and then protecting our estuaries. One of the main problems with all of these things, and the Dutch have seen this also, is that you really heavily influence the flow in your estuary. And unfortunately, if you have a place like Holland, very densely populated, these estuaries are economically very important. So we've got mussel cultures, oyster cultures, and this is the case in many estuaries, because you're always close to population centers, on the coast. This is, of course, an advantage of marine energy technology also, right? Population centers are concentrated near the coast, so if you can extract energy, that would be great. But the downside is that these estuaries often play a very important role, either because of harbor traffic, but also because of oyster fishing, or recreation, which is also important. And so this is one of the big problems, that you come in, no matter what you do, you will affect the estuary flows. And unfortunately, with a lot of these things, the models haven't been really good enough to assess this. This was the same in La Rance. They had models. Of course, that was in the 50s when they designed this. But they were very unpleasantly surprised when they put that in. In Korea, they're apparently running very, very complex, elaborate models of the estuary, but they haven't published that yet. But yeah, there is definitely a lot of interest.
And Laurent, how come they don't capture energy when the water is flowing into the estuary? How come they only capture energy when the water is flowing out?
That because they don't want to impede sediment transport and other things too much, right? I mean, if you start extracting it going both ways, then you're really closing off your estuary. You have a tremendous buildup of sediments right before and after the estuary. One of the problems they have now with the ebb tide is that a lot of the sediments don't flow out, right? And so you have a buildup of sediments in the estuary, and sort of you're killing your own resource, right? And as that builds up, then not as much water can enter, right? So this is one of the problems. So it was good news for the Dutch because they go with the little dredging ships, right, and dredge all that stuff out, okay? So I shouldn't complain too much. We've had a lot of work in Lance, you know. But of course, when you start dredging, you know, you can just imagine all the particles go up, and you're really just ruining all the flora and the fauna.
On this contraption you had before, you described as the snake, is that more reliable than some of the other rotational types of equipment that have been deployed so far?
For wave energy, it's pretty robust, the Polamosh. The Polamosh, if you're looking at the wave spectrum, which it can get power, it's not as great as you would hope, but they can get energy, reasonable energy, out of a very, very large wave spectrum. So you could put it somewhere and basically use it, although if you have seasonal waves, then obviously you will see some reduction. If you look at capacity factors of the Polamosh right now, there's not much information out there. Capacity factors are similar to wind turbines for good waves, for the high resources, about 40%. But if you're looking at these lower resources, then it drops down to 20%, 25%. So they still have some problems, but they're pretty robust. The Polamosh is more robust than some of the other devices out there, but the power buoy and wave bob are doing pretty good also right now. And the difference is, do you want to have something on top of the water, maybe impeding boat traffic, or do you want something in the water column, maybe having some other consequences? No.
You had comparative figures for power density for solar, wind, so
Yeah.
on. And I wonder if you could say a little bit more about how those are determined, what they mean.
The wind and the solar power densities are quite well known. And I just looked here at the optimal resources in the United States. So for wind, I used the Great Plains. For solar, I used the desert states. The others are estimated using the formulas that I gave you. So for tidal flows, it's basically done based on models, computer models that are looking at generated tidal currents. And for the waves, it's HF radar or wave buoys. That gives you a wave spectrum, and then you're using the formula h squared t over 2 to get an estimate.
Your wave power units were like for kilowatts?
Per crest length, per meter, yeah. So you see this as per meter. Square meter. Yeah, so if you're looking at solar, they always give it in terms of square meter. So for example, for solar PV, just how much, yeah. They're different units, so it's a little bit hard to compare. If you're looking at power density of tidal currents, of course, you're looking at it per surface area in the vertical, right? So not per surface area in the horizontal. So these things are very hard to compare, but it would be much nicer if you could say what are the ratios of cost per kilowatt or so. And I can't give that right now because nobody will tell me what it is for these wave or tidal energy devices. My estimates are, from looking at the very little that I can see, is that it is quite high. Now maybe 25, 30, up to 40 cents per kilowatt hour. Compared to wind, which is down, sort of between 4 and 8. And solar is still reasonably high up, but probably less than that for solar PV. So it's really very high. The costs right now are very high. So this is also the reason why the only way we can enter the market, really penetrate this market, if we had feed-in tariffs, for example, which they just passed November 26th. The UK passed feed-in tariffs. There's been a really, really big debate for years. They never wanted to do this. They were like us here in the States. We have renewable portfolio standards, and they have the same called an RO in Britain, but nothing like feed-in tariffs. But they've just now started, and maybe we'll do the same here at some point. Yes?
We should probably stop.
Okay.
At this point.